Hello, hello.
Yeah, okay.
That already is
Okay, welcome back. We're delighted as our second speaker this morning on continuing the. I guess we're not talking about spins actually. Okay,
it is spin, but it's not spin liquid.
no, okay.
Yeah.
So anyway, Peng is going to talk about his work on the anomalous and topological Hall effect in quantum materials. So thank you. Peng is here from Rice University. First visit to Knesset in the city. We're really happy to have you. Yeah, great.
Thank you. Yes, thank you for getting me here. It's a great venue. I learned quite a bit already in the last few days here. Yeah, I'll actually talk about something that's actually brand new. I mean, we just submitted the paper. So most of the talk will be on stuff that's yet to be quote unquote completely vetted. So I wanted to sort of sort out and to get impression of sort of the story we have on the system. Yeah, so this work is mostly supported by DOE, which Laura nicely reminded me I put the wrong sign. Oops, oops. I thought I tested it was working.
Yeah, oh, sorry.
You might need to just click on the screen.
Oh, click on the screen.
Yeah, just so you've got focus. Yeah, just so it focuses on it again, and it should go.
Oh, yeah. Oh, okay. Yeah, so this work is mostly done by my group members and Yao Fengxie, Shi Jiexu, and then we initially started with Claudia's a group at Max Planck, and then the theory was actually mostly done Naoto Nagaosa at RICAN. And when I visited Japan, thanks to ANCAM last year, when I visited Japan, and then we discussed the sort of the theory aspect of it, and this is how this work sort of started. Let me quickly review sort of what is what we typically call a very simple ordinary Hall effect, right? Everybody knows this very well. And for any sort of metal, if you turn on a external magnetic field and put a current, then you'll see sort of a so-called Hall voltage, and that's very well known for more than a century. And now, if you think about the system as having sort of an anomalous Hall effect, and what you can think about,
we're getting the note page on Zoom.
Oh, how do I? You have to share the whole screen?
You can share the window and not the.
I thought I shared the window.
No, that was free.
It took me 10 minutes on Monday.
Go to shop, stop share.
Stop share.
And then reshare again.
Okay.
Okay, now you have to get out of the PowerPoint first. So you can see the. Oops.
Stop the PowerPoint.
Oh, let's stop.
Well, that's maybe I'll tap and get you to Zoom.
Oh,
Sorry, it's taking.
It's not clear that this is harder than.
this is much harder than.
Maybe there's some escape, no escape.
I did escape.
Doesn't
happens.
Which button do I put actually? Connect to an external. Not textbook to learn.
Maybe Frank will come up.
Right, yeah.
I don't know Windows.
Keeps changing. Without, there's a different thing that's.
Oh, yeah.
Yeah, imagine if the laws of physics change.
There was no cursor.
Yeah.
The laws of them change.
Well, as some people.
Oh, no.
That's there's something, but I don't.
What about the bottom left?
There is no cursor on the screen.
No, on the bottom left there is.
Well, that's.
Yes, but not.
Oh, no, here.
Thanks for that.
Okay, so now I share again, right?
Yes, and now choose screen one.
Screen one. Okay. Sure.
Looks like it's coming.
No, that's the wrong. That's not a note.
This is screen so you're sharing.
Oh, maybe I should just change here, display screen setting.
Yeah, screen two.
Do not present a view and slideshow. No, no.
Now
That's swapped it. No, you don't want to do that.
Now you're sharing the right one on Zoom. If you, oops.
Yeah, stop the share.
Try to hit this stop share maybe. Yeah.
Where's the mouse?
Yeah, it doesn't show your problem.
Sorry about that, yeah.
No idea. Maybe I
Oh,
can.
maybe.
I can.
Recording in progress.
Good.
No, we still have the presenter.
It's good on those.
No, it's the wrong way around.
Duplicate.
Duplicate.
Okay, that's good.
That's looking better. Yes. That's looking better. You hit play, but it's hit play.
No, I think it's still the same problem.
Oh, still.
So let's see.
That's good. That's good. That's good. That's good.
Oh, is it? Oh, just was delay. Yeah, perfect. Sorted.
Thank you.
Okay, yeah, sorry about that. Just click on the screen.
That's good.
Okay. Yeah, so for anomalous Hall effect, I mean, what you have to have is some additional field, applied on the system, either internally or externally, to give you additional term that's not really sort of what we call the ordinary Hall effect. For example, if you have magnetic textures or ferromagnet or other things that can give you this anomalous sort of signal contributing in addition to your regular Hall effect. So one of the sort of the famous ones that are known to give rise to so-called topological Hall effect is so-called the sort of skyrmion lattice. And skyrmion is nothing but the sort of a curl of spins that is actually topological, and then can give realize a fictitious field that can contributing to the regular Hall effect. And one of the key features of a magnetic skyrmion is the so-called spin scalar clarity, which essentially is nothing but the 3 spin correlation function. So you basically have 3 sort of near spins with Si dot Sj cross Sk, and when that's not 0, that gives rise to a contribution to the so-called topological Hall effect. And this quantity is also a scalar that actually measures the time reversal symmetry breaking. So the other way, of course, they can give rise to additional rather than the additional Hall effect is a so-called ferromagnet. That's actually quite sort of a conventional. And then the third one is you can think about when you have a Berry curvature in K space, and that can potentially give rise to additional contribution to the Hall effect. And this is actually basically arises from the well semimetal, and you have this 2 point that can give rise to anomalous Hall effect. So very recently, a bunch of arguments suggest that when you have a band splitting from outer magnet, that can also give rise in terms of additional contribution to the anomalous Hall effect. So all of these ways of giving additional contribution to the Hall effect, basically you have to have several things. Either you have to have a simple ferromagnet, and that breaks the long range order. And then you have so-called skyrmions. You have 3 spins that give rise to additional contribution to the spin scalar clarity, or you have some sort of band splitting, and can give rise to additional contribution to the Hall effect. But all of this actually requires the system to be either frustrated, or you actually have sort of a so-called long range order. So these are sort of a bunch of examples that can give rise to anomalous Hall effect. For example, if you have frustrated spin, and in this case, a 3 spin can give a non-zero spin scalar clarity, and that can give contribution to the anomalous Hall effect. And all of this actually happens either deeply inside the magnetic order phase or very close to it. There hasn't been really an example of a sort of a collinear antiferromagnet in which when you stay at a temperature well above Tn, you can still have contribution to the anomalous Hall effect. So these are sort of all the examples that we know of that can give rise to this. So this is sort of this is another example that people have known. So you either have to have some ways to produce internal field that can give rise to anomalous Hall effect, and then it's unlikely to happen in the paramagnetic state well above Tn. And it's particularly unlikely to happen in the collinear antiferromagnet. That is not the outer magnet. And in the collinear antiferromagnet, of course, spins are completely lined up, and your spin scalar clarity, it's going to be Si dot Sj cross Sk is going to be basically 0. particularly for system above Tn, there's really no spin correlation at all. You would expect, nothing actually happens in those regimes. So I'll actually show you an example that's actually contrary to everything, that we know of. And then, we actually see really very large anomalous Hall effect, and we'll try to provide a microscopic understanding of why that is the case. So if you think about the, a system that has a long range order, I mean, you can essentially think about, for any sort of a system have a long range order, and basically what determines the order? It's basically nothing but a competition between the exchange coupling and your thermal energy. I mean, you can basically write down, the Hamiltonian as, as Si dot Sj, and cross, Jij. Jij will be the exchange coupling of the spins, nearby. And then in the case of a ferromagnet, you have a one sign larger than 0. In the case of anti-ferromagnet, you're going to have Jij equals to, less than 0. And even though the spin Hamiltonian can be written in this way, you basically describe an order parameter is basically think about as an average S, right? You typically measure the order parameter with neutron scattering. You basically look for Bragg peak, magnetic Bragg peak, and you look at the order parameter. You say, I have mean field theory, and I have magnetic long range order, and I basically describe the spin system, as having basically in a simple ferromagnet, your average spin align on the same direction, where the order parameter is basically characterized by finite single spin, expectation value Si. And in the case of anti-ferromagnet, it's the same thing, but I still actually describe the order parameter by average, spin value Fij. And this basically tell me I have a spontaneous, symmetry breaking. But you see, in the case of both a ferro and anti-ferromagnet, and what really determines the magnetic ordering temperature is actually two spin correlation function between Si dot Sj. So in this situation, this is what I simply call, once you have this, a simple order parameter Si, and you can also think about the, two spin, composite order parameter. Instead of thinking about a single order parameter Si, you could have a situation, in which your your anisotropic, two spin correlation function, Si dot Sj, in different directions. For example, when you Si dot Sj in different directions, that basically means, Christophically, you have a spin-spin correlation function along A and B and C direction of a typical crystal. And this not necessarily, have to be 0, when your average S is 0. And this actually phenomena is well known, it's typically called, sort of a spin nematic phase. Basically, you have a breaking of a symmetry in spin space, but you actually still have a situation where your average S is actually a 0. And this was actually known for many sort of years. So this actually is somewhat different from what typically we call, electronic nematic phase. It's very well known in the case of cuprates and nictide and so on and so forth. In the case of electronic nematic phase, that typically happens in a system that has, a ground state that has typically very close to a tetragonal, but not exactly tetragonal system. That basically means that, when you go below the ordering temperature, your rotational symmetry of the system is actually broken. It's not a C4 rotational symmetry. But the case of a spin nematic phase, you actually can completely happen in the case of a completely tetragonal system. So what I mean by that is that let's just simply think about this particular material, yttrium, manganese bismuth. It has the crystal structure so-called the C-type. In the case of a C-type magnetic structure, your spins are basically, some are top, one in down, and go up and down is a simple anti-ferromagnet. Of course, in the order state, we can measure the average, the moment that is, not 0. But in the case of, above the ordering temperature, and you can think about the system as, sort of a vibrational spectra. And this vibrational spectra is typically we call sort of a spin wave. But in the case of a, paramagnetic state, you have what we call spin fluctuations. And these spin fluctuations, will have a directional dependence. And that basically means that you can potentially have spin space anisotropy, basically meaning the vibrational amplitude along A and B and C axis, doesn't have to be the same, even when the system is completely tetragonal, particularly in the case of AB. A very simple example is shown, up and down, right? In the case of up, in a completely, paramagnet, you should expect, your spin fluctuations, be completely isotropic in spin space. But it doesn't have to be that case, right? You can have a situation in which your spin fluctuations between A and B are completely, different, yet the system still maintains the C4 rotational symmetry of the tetragonal lattice. Yeah.
Here and some comment that was different from electronic pneumatic.
Yeah, I'm going to come up with the next slide.
Okay, thank
Yeah.
you.
Yeah, so how is that different from electronic pneumatic phase? So a prototypical electronic pneumatic phase, I've done, necktie for many years. I use that as a sort of an example, right? In the case of necktie, you typically have a, what typically we call stripe and magnetic, long range order, which intrinsically breaks the C4 rotational symmetry of the underlying lattice. In the case of necktie, before the magnetic order occurs, you actually have a tetragonal to orthorhombic phase transition. And this phase transition actually breaks the C4 rotational symmetry of the underlying lattice, and then your long range order is established at a temperature slightly below or very close to the orthorhombic, tetragonal orthorhombic phase transition. So in this case, then you can have a situation in which you have so-called nematic regime, and in which case what you actually expect in this case is again there's no long range order, and you have M1 M2 that's not equal to 0. But in reciprocal space, what you're basically seeing is that this is our neutron scattering data, that in the order state you basically only see spin waves from two of those supposedly 4 peaks, because the system is actually orthorhombic, and that basically means your spin is only aligned in one direction. And in this situation, if you're doing an experiment at a temperature above the magnetic ordering temperature, you will still see a very small anisotropy between A and B. Yeah.
But you're not saying this is a fundamental feature of electronic pneumatic, right? Because
No, I'm basically saying that
it could happen in a tetragonal system.
yes. I mean, no, but in the purely electronic, in the electronic pneumatic phase would basically require you, when you rotate by 90 degrees, it breaks the C4 rotational symmetry. And in this particular case for the necktie, the reason this actually occurs at a temperature above the orthorhombic transition temperature is because when you do the actual experiment, you have to put unilateral string on the sample. And this anisotropy is actually broken by the unilateral string in the system. Laura disagrees.
Oh, I have these experiments that show you can see this without the actual string.
I see. Okay, yeah. But at least in the neutron scattering type of experiment that, we believe this is actually due to unilateral string, because in a true tetragonal system, you would expect, all electronic properties to follow the C4 rotational symmetry. For the spin nematic phase, you don't have to have that. And that's sort of my key point. So now, if you think about a spin space, anisotropy, of course, it's a two-spin correlation function, right? As I mentioned earlier, your spin scalar polarity, which measures time reversal symmetry, is actually a 3-spin correlation function, right? And in principle, your 2-spin correlation function should have nothing to do with 3-spin correlation function. So when you have this so-called spin nematic phase, basically you have a spin space anisotropy that in principle should not give rise to anomalous Hall or anything associated with that, right? And that's in principle, should be true. But I'll show you an example. Under certain circumstances, you can actually violate that. So let me now talk about the material that was, I'll be sort of the key focus. So this particular material, what we're interested in is the so-called yttrium manganese, bismuth 2, as I mentioned earlier. And this was actually discovered, I guess, about 10 years ago. By Petrovic's group in the Brookhaven, and they've done basic characteristic of this material is what typically people call C-type antiferromagnet. It's strictly central symmetric, and then it has strictly tetragonal. And you have a sister materials that's including the strontium and calcium and manganese bismuth, and they all have the same sort of a magnetic structure. And what is really, sort of started this whole discussion started from this very interesting angle resolved photoemission spectroscopy paper by Borisenko, where he actually claimed that the neutron scattering and other type of measurement were incorrect, in the sense that this is not actually strictly a C-type antiferromagnet. Basically, it's not a Dirac magnet, but rather is well semi-metal, in the sense that he claimed to see well points, at least from angle resolved photo emission perspective on the surface. And the consequence of that is that you should expect to see a small canting of the moment deviating away from the c-axis, standard c-axis antiferromagnet, and basically give rise to an internal field, that can particularly give rise to the anomalous Hall effect. So this was sort of a basic experiment published like 2-3 years ago by Claudia Felcher's group that was inspired on neutron scattering work, and they actually published in Nature Materials basically a claim to have found a giant anomalous nerve signal in this particular compound at a temperature actually in the neural measurement at a temperature much higher than TN for this particular compound, which is about 300 Kelvin. And they again use the same argument, saying that this is actually a well semi-metal instead of a Dirac metal. Yeah, so this is basically sort of their thermal transport data, basically claiming to see this very large anomalous nurse effect. And then I mean, for that to actually happen, you really need sort of a so-called a non-zero spin scalar sort of clarity to be a non-zero in order for this to actually happen.
In what sense is it anomalous? Isn't Claudia applying magnetic field?
You can either apply you do a temperature gradient and then you apply magnetic field, or you can put a electric current, apply magnetic field. In both cases, it's actually anomalous Hall effect. I'll show the data a bit later.
Maybe it's
Yeah.
semantics, but I thought you said it yourself. Anomalous means no magnetic field applied.
Yeah. Well, it's basically extracted to zero field.
So could you show the data?
Yeah. I mean, you have this turn, and then you use the slope of the higher field, and then if you extract it to zero field, then it's there. Okay. So this was actually in quite of a contrast with neutron scattering work, and this was done by Andrew Boothroyd's group, and he looked at all of this compound, particularly focused on this compound published like 4 years ago on this yttrium manganese antimony 2. And he, gave rise to this different possibilities. The claim by Opus measurement was that this is actually a well semi-metal and should have a canting of the moment, away from the c-axis direction instead of a gap Dirac semi-metal. And this is not supported by neutron scattering. So he looked at the polarized measurement and all kinds of measurement. Basically, he claimed there's zero evidence for canting. Basically, it's a strictly C-type antiferromagnet. He gave I don't remember the value, that it's a very, very small value to be a few degrees, the very, very small angle of canting is possible. And there's a further measurement he's done, further inelastic scattering measurement on this particular compound, and then he basically completely Andrew Boothroyd basically completely determined the heat coupling along J1, J2 and J3, and you can see the spin wave are very well gapped, about the 10 millivolt gap, and then the bandwidth is roughly about 60 millivolt. Oh, basically he claimed that if the canting is there at all, it has to be less than 5 degrees based on the fitting of the the neutron scattering spectra that he's getting. And similar compound, similar work has been done on the strontium and calcium compound. Again, there's actually no evidence of the canting whatsoever. Okay. So and this is from a Brookhaven group, again from Chonghuada and Zaniniak, basically looking at this particular compound, a spin with very similar result as the result of Andrew Boothroyd. So now let me show basically the raw data. We sort of started this, initially realized that this yttrium manganese bismuth would have this very large anomalous Hall effect at a temperature well above a TN, which is 300 K. We thought, what's potentially going to happen, if you, instead of using yttrium manganese bismuth, you're doing the same thing with the calcium manganese bismuth, because in principle, both of the system, would be exactly the same magnetic structure, right? Whether the calcium would have the same thing. And we actually did the, transport measurement. I didn't do the transport measurement, so the collaborator, and also my group actually did the calcium, but mostly the Claudia Felcher's people did the yttrium. We compared the data, we don't see anything like that in the calcium, sample. And basically, once we summarize all the result, we plotted this in terms of anomalous Hall effect, and it turns out this anomalous Hall effect is really in the intrinsic regime. And you can see an order of magnitude larger anomalous Hall effect in the case of yttrium as compared with the calcium manganese bismuth. And this is not understood at all. So then, you can see basically, really this anomalous Hall regime. And again, the Tn is roughly around the 300 Kelvin, both for both the calcium and yttrium compound.
So does that mean that the d electrons of the ytterbium are playing a role?
Because naively, if you only look at the compound counting the electrons,
Yes.
the ytterbium is supposed to be non-magnetic.
Huh?
But you're right, that turns out to be wrong.
Oh, so it's the F electron.
There's actually F electron.
I see.
Yeah, I mean, if you only count the electrons, I mean, so far nobody actually have done the measurement to show that the ytterbium actually has a moment, but we show the ytterbium actually has a moment. And this is sort of the central part of the story.
And therefore the electron count won't be the same, because you shouldn't count the moment as an electron.
Yeah, so let me continue. So yeah, this is basically anomalous Hall, and you can basically see, but that's actually just seeing anomalous Hall, below a magnetic order, a sample is not that surprising. But what's really surprising is that this anomalous Hall seem to be, occurring actually maximum, at a temperature around Tn but above Tn, and then it crashes away roughly around 400 K, and that's actually the maximum you can measure with a ppms, and then actually goes away at low temperature. This, is very, very strange, right? And I can show you the Tn for yttrium is 300 K, and Tn for calcium is like 295 Kelvin or something like that. And there's actually an order of magnitude difference between these two compounds. So how do you actually understand that? So we can actually, instead of doing unpolarized neutron scattering, we can actually utilize neutron polarization analysis to actually completely determine in both the magnetic order phase or as well as in the paramagnetic phase, the spin space anisotropy of the system. We can just completely determine it with polar neutron, because I mean, I don't think most people are neutron scattering expert, but you have to trust me, we know how to do neutron scattering. Basically, you can shoot a neutron, but if the neutron polarization, neutron scattering has a particular feature. The neutron scattering, is only sensitive to the moment perpendicular to the momentum transfer Q. It is also only sensitive to neutron, spin direction, perpendicular to neutron spin direction. So if you do a spin flip scattering, basically, if neutron, coming in with a particular spin direction along Q, if the neutron, flipped 100 degrees, you're basically going to be probing all the moment perpendicular to that flip direction. But you can do the same experiment. Instead of aligning the neutron parallel to Q, you can measure perpendicular to Q in one direction and perpendicular to Q in the other direction, and you can basically completely determine, within that particular geometry, that what the moment lies, in which direction of the moment lies within the Q that's within the perpendicular to the Q. You can basically determine where MA and MB and MC is if you measure enough, Q points, because neutron scattering can only measure a moment perpendicular to Q. So measuring one Q is not sufficient. So you have to measure several different Qs, and then you can basically completely determine, MA and MB and MC. And you can basically not only determine that, as a function of temperature, you can determine that as a function of energy, and therefore completely identify whether there's actually a really spin nematic phase in the system or not, as you gradually go down from high temperature to low temperature. So this is exactly what we did. We did two things, right? The first thing we did is to basically try to confirm that whether the system really is a well semi-metal, basically meaning there's any Yeah.
Is there like a set number of Q measurements or is it sort of trial and error until you feel like
No, it's actually overdetermined. Typically, we measure equivalent Q. I mean, if you do all the neutron scattering cross section, typically 2Q is sufficient for you to determine MA and MC. But we always overdetermine. We typically measure 3 or 4 Qs, and then because the form factor is slightly different, but you can account that. So then you basically completely overdetermine. Yeah. So and the first thing we want to do is do elastic neutron scattering. It's completely identical to inelastic neutron scattering, except with no energy transfer. So in that situation, the first thing we wanted to answer is whether there's actually any implant moment deviating away from the C-type antiferromagnetic order. So basically confirming this can potentially be a well semi-metal, at least in bulk, right? So we've done a complete measurement with X, S, Y, Y, Z, Z, and then we'll look at all different Qs. We find no evidence of any magnetic moment in the plane. And the upper limit for canting, my student told me, was basically less than 0.03 degrees. And that's actually the limit we can do. So basically, it's a strictly C-type antiferromagnet magnet. And this is for the ytterbium compound in the ordered state. And it's also not a ferrimagnet. Because there's also possibility that if a C-type antiferromagnet, right, the moment along one axis can be slightly different from the moment on the other axis, right? We can completely eliminate that possibility as well by doing neutron polarization analysis. Okay, so that's the first conclusion. So it's a strictly C-type antiferromagnet. And we repeated the same measurement, for the calcium, it's identical. There's just no possibility for a canting, and no possibility for Wilson metal, and no possibility for a ferri component along the C-axis. Then we decided to do inelastic neutron scattering experiment. Again, like I mentioned earlier, for doing inelastic neutron scattering measurement, you basically you can do it below and above the transition temperature, right? Below the transition temperature, what do you expect? You'd expect to recover the unpolarized neutron scattering measurement of Boothroyd and the Brookhaven group, and basically seeing a fairly large spin gap. And you should also expect, because the magnet is believed to be the local moment, you should expect the vibration spectra to be entirely along the direction perpendicular to the ordering direction, right? And this is what typical of transverse spin waves, right? So we did X and Y and Z, and as I mentioned to you earlier, since the moment is entirely along C, so we should expect the C-axis component of the spin fluctuation to be zero below the ordering temperature, right? Because the local moment cannot modulate along the C-axis, so you can only have vibrational amplitude amplitude along the A and B direction. And this is exactly what we see. You don't have to look at the detail of the neutron scattering data. We look at different Qs, and when we completely resolve it, you can basically see that really the spin wave gap is gapped, above the gap. It's really a transverse spin wave, and that's basically have an A and B component that's identical. So basically, you have equal amplitude of vibration along the A-axis, and this is the real space A-axis, and then on the B-axis. So that's actually, very well, sort of suited and taken care of. But what's really surprising is that you now go to a temperature 300 Kelvin, which is roughly, a couple of Kelvin above the Néel temperature. And now you can see that if you completely resolve MA, MB, and MC, you can clearly see that MC is different from MA and MB, but MA and MB, you can remember MA is the blue and MB is the orange. They're clearly different below roughly 4 millivolt, and they're actually identical above 5 millivolt. So what this is telling us is the system is actually a true paramagnet on a time scale of more than 6 millivolt, but start to be anisotropic in spin space, below 4 millivolt. And you can do this as a function of temperature. You warm to 400 K, you start to more or less to be isotropic. By the time you warm up to 450 K, and that's the highest temperature we did, is completely isotropic. So we therefore have identified a spin space anisotropy that's actually changing from 400 K to 300 Kelvin.
So should be looking at which result of data.
Yeah.
If I look at the
Oh, you should only, the top two panels of raw data should completely ignore. You should trust that we know how to do the convolution, and then you should only look at the data, we convert it into MA, MB, MC.
So if I look at that at 230 Kelvin, isn't MA on top of MB?
Yeah, that's expected, right? Because you have transverse spin waves. The TN is 290 K. So your spin wave is basically transverse spin wave between A and B should be completely isotropic, and you don't have a amplitude modulation along C.
Oh, so it's only in a paramagnetic phase.
Yes.
What is
290.
So 300 Kelvin is what that's the.
Yes. And it disappears roughly around 400 Kelvin. And 400 Kelvin becomes isotropic at all energies that we probe. Okay. So yeah, this is sort of the story how we actually probe it, right? Because each time you probe it, you go to a Q, and then you can measure perpendicular, but you measure X, Y, and Z. You measure different component, and then you deconvolute, you over determine, and then you completely solve A, B, and C as a function of the temperature and as a function of energy. Okay. So if you do a detailed temperature dependence of a 2 millivolt excitation, I mean, it's too costly to do, at all temperatures, right? But for 2 millivolt, you can just set at 2 millivolt and do X, Y, and Z, and then do different Qs, and you can solve it. And you basically see it become isotropic at 450K, and then start to be anisotropic at 400K, and then sort of blows up roughly around the, Tn, and then finally at extremely low temperature, it sort of crashes down. And then if you do a subtraction of Ma minus Mb, and that's basically the spin space anisotropy between A, B axis, right? Even though the system is actually tetragonal, you can clearly see a transition roughly around 400K start up and then sort of blow up. And this is somewhat similar to what you'd actually see in the anomalous Hall effect. And if you do the same thing for 9 millivolt excitations, you don't see any anisotropy between A and B. Basically, nothing happens across Tn.
Pengcheng, just to ask you, so this is not that dissimilar from what you yourself measured in places varying 1 to 2. You go slightly above the from the
Yeah, I'll show you 1 to 2 data. I'll show you 1 to 2
you
data.
say in the X1, you see clearly an isotropy, right? This sort of ellipse.
Yeah, but this is a much higher temperature regime. I'll show you next is going to be our 1 to 2 data, right? So what do we expect? What do you expect in the case of 1 to 2? I've measured it, I spent 10 years of my life measuring, 1 to 2 and associated compound, right? So in the case of 1 to 2, it's actually quite different. The way it's actually different is because you can think about 1 to 2. First of all, it's different because the system is actually orthorhombic. Below the nil temperature, it's like I mentioned earlier, it's really, sort of the EZ axis along A axis and B axis is the hard axis. A axis is actually long axis, right? And you can do the same measurement as you do before, but you can see clearly because A axis is long axis for any sort of a second order phase transition. If you expect a system that's sort of a 2-dimensional, phase transition of a 2D type, you should expect always the divergence of the spin fluctuation along the longitudinal direction, meaning the ordering direction, and then the transfer direction both should do nothing. Because in the case of Baron 1 to 2, your long range order direction is A-axis direction, right? So if you measure MA, MB, MC, and you can basically see that the very narrow regime, maybe like 10-20 Kelvin regime around, and you can see this divergence of A, and then B and C does nothing, and then crashes down.
But crucially, Ma is not equal to Mb, even above neo temperature.
Yeah, well, no, I'm saying it's in a very, very narrow regime.
Right, that's it. Right, so that was exactly what I was trying to ask.
Yeah.
Isn't what you see in turbulent manganese bismuth not the same?
No, because the temperature regime is much higher.
Okay, but qualitatively, I don't care if it's 20.
Yeah. Well, I mean, but the system. The other thing that's really different between Baron 1 to 2 and yttrium manganese bismuth is that yttrium manganese bismuth it's entirely tetragonal at all temperatures, and this system is actually orthorhombic. You have a sort of so-called electronic nematic phase rotating 90 degrees would be different, but in the case of yttrium manganese bismuth is tetragonal throughout. So in a systematic 2-dimensional long range order, you should only expect the divergence of a C, AB should be the same, and then crashes down. Yeah.
So yeah, the 1 to 2 also, it's not only closed, right? But 1 Kelvin apart, but it also tracks each other if you tune with some other parameter.
Yeah, I mean,
so what happens here if you apply pressure or whatever?
That has not been done. That has not been done.
But these could, in principle, not track each other. And
yeah. I mean, in the case of 1 to 2, this particular paper, we're actually talking about uniaxial pressure. If you put a uniaxial pressure down, you can actually modify all of this component. But it's purely due to the exerting of external pressure. I mean, in the yttrium manganese bismuth, that has not been done by anybody, as far as I know. Yeah. So this really tells us that this phase transition is actually in the purely tetragonal system, you clearly see spin space anisotropy established at like more than 100 Kelvin. I mean, your critical regime typically is very narrow, right? 10-20 Kelvin above at most, right? 10-20 Kelvin above transition, but we're talking about 100 Kelvin, above the neo temperature of 290 Kelvin. So how do you actually understand the anomalous Hall effect? Before we do that, we can also do polarized is too costly, right? So we can also do unpolarized neutron scattering measurement basically looking at to see, whether you have spin correlations, above the nil temperature. So in this situation, we basically use ampolla measurement to completely map out the entire reciprocal space. And the top panel shows the entire reciprocal space, as a function of energy and momentum along the in-plane direction. And then the bottom shows the reciprocal space along energy and momentum along the c-axis, right? You can clearly see that you roughly have a 2D to 3D transition, roughly around 400 Kelvin. You can see excitations is completely, smeared along the c-axis at the 450 Kelvin. Now you can see this is the L direction. There's basically nothing there. But then by the time you cool down to 350 to 300 Kelvin, 350 Kelvin, you now to see both modulation along C and in the AB plane. And in the AB plane even survive at 450K. So this basically tells you spin excitations are highly two-dimensional, sort of really survives in the AB plane, but along C-axis, you basically have a 2D to 3D transition, roughly around sort of 400 degree Kelvin in the system. And you can basically measure, different temperature and then really look at the coherence and so on, so to determine that to be true. So the other thing that's really interesting is that now with unpolar neutron, we can have much more flux than we have with polar neutron. You can see this gap even at 270K is not completely closed. You still have a bunch of states within the gap, which is much more precise than with polar and neutron scattering you can measure. So to summarize what we actually obtained, we actually measure spin space anisotropy both as a function of energy and as a function of temperature. You can basically derive the entire observation using this sort of a scheme. And high temperature is paramagnetic, and then roughly around Tn, you have a very strong spin space anisotropy between A and B, even though the system is purely tetragonal. We did a very careful crystallography to prove it's tetragonal. And then below Tc, below Tn, you basically see this anisotropy, and this is sort of the high energy. And this is a paramagnetic state, and then the lower. This is basically a schematic picture of what we're seeing. We're basically seeing A and B are quite different in spin space. So this still does not answer our question, right? Why the anomalous Hall appears at such a high temperature, even though it's very tentative to suggest that these two things are, maybe somewhat connected. So this comes, to appears as a sort of question, right? So previously, people thought, ytterbium manganese bismuth it's actually sort of 2+. But we've done a very careful measurement to actually show more than 50%, roughly 50% of the ytterbium ions in the system is actually sort of 3+. So therefore, if you think about this, then you can essentially think about the system is having two spin correlations of the manganese can potentially interact with the spins of ytterbium and to form a 3-spin component that can potentially give rise to the so-called dynamic spin scalar clarity that does not equal to 0. I mean, of course, the anomalous Hall effect is obtained by applying a symmetry breaking field in the plane. So your external magnetic field is basically acting as a sort of a direction of the spin clarity. Basically, polar. I mean, because when you put an external magnetic field, you always polarize the ytterbium moment, right, along the field direction.
Just to clarify, do you see any static moments on ytterbium?
No, there's no ordering. There's no static moment. Nothing. There's no moment from ytterbium whatsoever. I mean, we don't actually no order moment. Actually, be more precise. I mean, the moment is determined from chemical analysis and spectroscopy analysis. So then, and this is where Naoto Nagaosa came in, right? He and his sort of a postdoc, and they did a detailed sort of a analysis. And basically, what they argue is that if you look at the in-plane magnetic field, and if you think about the spin nematic phase of the system is coupled with the formation of your spin space anisotropy along A, B, and C direction, you form these sort of a triangle as it's a 3-spin correlation function for in-plane magnetic field can be summarized along the A, X, and Y, and Z direction. And then you look at the order parameter system, you basically see it's always there at all temperatures, but below the nematic temperature, it's dramatically enhanced. And this should not happen in the case of a calcium doped compound. So this basically provided a very natural, this basically provided a very natural explanation of why the anomalous Hall, occurs at such a high temperature and why actually it disappears at low temperature. Because at low temperature, of course, your spin excitations are completely gapped. Even though your ytterbium moment is still there, but there's no moment for it to interact with. Basically, it should actually really suppress at the lower temperature. And this anomalous Hall is basically associated with what I think about is dynamic non-zero spin scalar clarity, and that essentially arises from interaction of ytterbium with the manganese moment dynamically. And at low temperatures, especially below 100 Kelvin, the gap really opens, everything is suppressed. So this, we look at the literature, we actually could not find any literature that discusses this, and this was our hypothesis that suggesting basically a new way of producing sort of anomalous Hall effect at actually temperature well above room temperature, and it's not coupled with any static long range order. So we thought this is a very sort of very cool, and basically this is a way of both connecting a two-spin correlation function with three-spin clarity correlation function with the existence of a magnetic iron in the particular system. Yeah. So how much time I have?
Okay, so let's see, we started around
11.
11, so we're up to
A little over half an hour.
Oh, okay, yeah. No, so I'm speaking too fast. Yeah. So this is basically the key. Yeah.
What does it? What are the results?
I'm sorry, I couldn't hear you.
The calcium.
Yeah.
Act the same way as the atrium. How does it act? What were the results like for calcium?
Oh, the calcium has no anomalous Hall at all. The one order magnitude lower. This is the data, right? The calcium data is in the blue.
Yeah. So for the previous, on the previous.
Oh, you mean the yin neutron scattering? You mean the yin neutron scattering measure? We have not done calcium, but I assume it's the same. I assume if you do it, it will be identical to. It's quite costly. We spend like about more than a month of neutron time to do all of this measurement. Yeah. No, I assume it's the same. Yeah. Because we did it elastically, but we haven't done the inelastic measurement. Yeah. Yeah.
Sorry, quick question. So earlier you claimed that there's no bias.
It's not a wild center level, no. Because there's no canting. There's no canting. It's strictly collinear.
How does this order parameter couple, right? Anomalous Hall electronic property.
Sure.
So this order parameter needs to.
It's coupled through the external magnetic field. Yeah. The direction is coupled through the external, because the anomalous Hall only appear. You have to.
Do we know how what the if I have a wire with a magnetic field, I know how to do the anomalous Hall. In this order parameter, with the electronic fluctuation or the electron bands, which then give you the anomalous Hall.
Oh, you mean the electronic structure of the stuff?
Yeah, the anomalous Hall is from the.
Well, no, we're actually arguing that we're actually arguing anomalous Hall effect in this particular case coming from spins. From scalar spin clarity is a sort of real space. Dynamically, it does not coming from the bands.
It is the electrons.
Yeah, sure. But it's just
somehow it has to, in some understanding it has to come from.
Yeah, you can sure. You can essentially think about that for example in this case of skyrmion, right? Skyrmion, if a real space spin a non-spin space clarity give rise to a fictitious field that affect the electrons, right? And we're thinking about the same way in this particular case, but dynamically. That's sort of the picture, yeah.
Trying to understand, this is very interesting, and I'm trying to understand what this order parameter means. So it's a three it involves three spin correlation.
Yes, yes.
And those I, J and K, are any three spins in the unit cell or? Are
No,
they-
this yeah. So these three spins will be two spins coming from the manganese. One of the spin will coming from ytterbium.
And that, would you say that respects C4 symmetry even when the coordinate parameter is finite? Or?
Yeah, in respect to C4 symmetry. But what's breaking it is an external magnetic field. It only occurs in the in-plane magnetic field.
Right, so when you apply a magnetic field, because that coordinate parameter is finite, then you break C4 symmetry.
Yes.
Thank you.
So, okay, and what's the evidence that this order parameter is finite?
Oh, you mean what? I mean, you mean the spin nematic order parameter? Oh,
Correct. Well,
I mean, we actually measured it, right? I mean, this, we actually measured the spin space anisotropy.
not schematic.
Okay.
How do you know purely from experiment
Mhm.
that ytterbium is not collinear to the two manganese and forms this aside of this chamber?
Oh, well, no, what we do know is that the ytterbium moment has to follow the external magnetic field. Yeah, ytterbium, because it's a free arm. The exchange coupling between ytterbium is minimal, right? So ytterbium has to follow external magnetic field, but the manganese does not, because the manganese has a spin space anisotropy. So we're basically arguing that it's the manganese spin that couples with the ytterbium moment dynamically that forms this non-zero spin space, a spin scalar anisotropy, a spin scalar quantum. I mean, this is a J called that. Yeah.
But this is always a value that doesn't fluctuate, right?
No, we're actually because we're actually talking about in a regime that's actually above Tn. So everything is fluctuating.
But this S cross S will also fluctuate.
Yes, it's a dynamic.
But then when you add magnetic field, get something.
Yeah, well, I mean, it only breaks the C4 rotation summation when you turn on the external magnetic field in the plane. Yes.
But just to understand,
Yeah.
the experimental statement is that you measure anomalous Hall effect,
Yeah.
and then you argue that it's due to this spin scalar angle, scalar spin chirality.
Yeah.
But then one could ask, okay, but is there an independent measurement of scalar spin chirality that tells you this actually non-zero?
Well, I mean, we know what's non-zero is the spin nematic phase, right? And we also know it does not occur in the case of calcium.
Right, but that's exactly what I'm trying to connect. What does this AB spin nematic, the MA not include NB? How is that connected to the
Oh,
chirality?
Yeah. This, well, I mean, I'm not a theorist, right? This is they have Naoto Naga also have a detailed derivation, from Landau's order parameter argument, and he plotted all the sort of the directions of the triangles and so on and so forth, and he basically based on that he argues that if A and B MA does not equal to MB, then you have a coupling between them, and then this coupling will give rise to an enhancement of the Anomalous Hall. Yeah.
I may comment, it always has to be a bit indirect because Neutron's Latin measures 2-point correlators.
Yeah.
And these are 3-point correlators.
Yes.
You're never going to measure that.
Yeah, you're never going to measure that. Yes.
Measure the effects of it.
Yes. But it's very tentative, right? Based on the neutron scattering measurement, that we see this, clear spin space anisotropy at a temperature regime is very, very close to that. And also the fact that the ytterbium has a moment that, based on this sort of symmetry analysis, it's very tentative to suggest that that's the microscopic reason for this to actually occur.
Just looking at the data, right? So you said the calcium system doesn't show an anomalous Hall effect.
Very small,
It looks to me the bump goes exactly over the same temperature range.
but it's extremely small. In order to magnitude lower.
It's not you. I mean, based on that, it's hard to argue that it has to come only from the ytterbium.
Well, I mean,
it's like a bump that it's the same temperature range. That's quite it.
yeah, but it's 1 order of magnitude smaller.
Yeah, but it's not an either or, right? So
What's the ratio?
Oh, I'm sorry, Andre?
Ratio to the calcium.
Oh, it's
Over
and we actually have a plot of the absolute value, the conduct. You mean anomalous conductivity, right? Yeah, here. So this will be the result for the ytterbium, and calcium will be somewhere here. So this is all the other compound that's been known. Yeah.
So were the experiments done with the magnetic field in the film?
Yeah.
Okay, because that was not clearly stated.
Yeah, no, it's, the anomalous Hall only appears when the field is done in the plane.
So it does not have any.
No, yeah.
And then to have a, finite, scalar spin karaoke, why does it need to have this anisotropy A and B?
Yeah, so this was like I said, this was Nagosa's analysis, right? So but
That's my
he,
question. Not supposed.
yeah, the theory. I mean, he actually did a detailed structure, detailed symmetry analysis based on the position of these three guys, and then he basically argued based on this sort of symmetry, and only when the MA does not equal to MB, you have this coupling. Regardless the theory, right? And the experiment is very tentative, right? I mean, it has the same temperature regime, and it does not occur, in the case of a calcium, or almost does not occur in the case of calcium. So it's very suggestive to say that this thing is associated with spin scalar clarity that is actually associated with ytterbium and manganese moment.
No, okay. Does it not worry you? Could you show again the next slide, the experiment? So I don't know. Yes.
Yeah.
Does it worry you that you see the signal all the way to, let's say, 90 Kelvin?
Yeah, no, it does not. The reason.
But your experiment about MA not equal and disappears. We're below what?
Yeah, no, I mentioned that, right? Because that was the polarized measurement. For unpolarized measurement, you can see, even at 270K. I mean, if the gap is not completely closed, so it's a fluctuating moment, right? So fluctuating moment, you can still have a little bit of stuff even within the gap. You can see even at 270K, you can. I mean, the polarized measurement is much less sensitive than the unpolarized measurement. Yes, but we know it disappears below 100 Kelvin, and when the gap truly opens, everything disappears. So this is sort of unpublished stuff in the case of ytterbium manganese bismuth. You have a question, Frank?
No.
So I hope I have like 10 more minutes or 15.
Yeah.
So then remaining time, I want to sort of switch gears, talk about another sort of system. It just got published like a few weeks ago on the early May on sort of a sister system. It's very. I mean, we've been working on the manganese, iron germanium and the CDW material for quite a while, and sort of as a companion system, I asked my postdoc to actually look at this ytterbium, iron germanium system, which turns out does not have charge order, but it does have anomalous Hall in a very similar way as the case of ytterbium manganese specimens. So let me show you this particular compound. This particular compound is ytterbium iron 6 germanium 6, and we can grow very nice crystal. It's a Kagumi lattice, and then we can do a very good transport. And unfortunately, this stuff doesn't have charge order. It's different from the iron germanium. But what's interesting is that even though the system does not have charge order, it has a so-called A-type antiferromagnet. And this A-type antiferromagnet is extremely simple. It's basically one layer ferromagnetic, the other ferromagnetic, and it's anti, in between layers. And the moment is exactly along C. But what's interesting in this particular material is that because the ytterbium is known to be 3+, so when ytterbium is known to be 3+, ytterbium again has no order at all temperatures. But because ytterbium has a 3+ moment, it actually can interact, with the iron moment. And it interact with the iron moment in a funny way. When you cool it down to below roughly 70 Kelvin, it rotates the C-axis moment to the plane. So you basically have a rotation of C-axis moment to the plane, and then you have a spin reorientation, due to ytterbium and iron moment interaction, even though ytterbium is not ordered, and they still have a exchange interaction between the two. So then we decided to do anomalous Hall on this particular compound, and then we did all kinds of anomalous Hall effect, and we basically find that these are sort of a typical transport measurement, and we basically find anomalous Hall when you apply an implant magnetic field, and we measure the Hall effect. Yeah, these are also the details very similar. We basically find anomalous Hall effect very much in the regime after the spin reorientation. At the lower temperature below the spin 40-50 Kelvin, and then a lower field, we see this very large. I mean, I don't know how large. I mean, this typical anomalous Hall effect. So this actually is sort of very, very similar to the stuff I talk about, the ytterbium manganese specimen, except in this particular case, it's in the long range order state. It's not in the paramagnetic state. So again, I think the argument here is very similar. So that even though ytterbium has no moment, the spin scalar clarity, because once it's reoriented into a collinear case, I mean, both in the case of A type and then once it's reoriented, it's still in the collinear case. So it's impossible to have a spin scalar clarity statically, but you can have it potentially through scattering of spin fluctuations. So we basically use the neutron crystallography to determine in above Tn, it's A type, and below Tn, the moment is still collinear. So therefore, your static order is impossible to give rise to a non-zero spin scalar clarity, to give rise to the anomalous Hall that's been actually observed. So there has to be spin fluctuation that give rise to this. So and we look at small with this one with neutron scattering, we basically find no skirmions. So statically, it's impossible to give this anomalous Hall. We basically confirmed there's no skirmions. And then we did the yin last neutron scattering experiment. We can clearly see as soon as you have this spin reorientation, and this gap disappears. Above the spin reorientation temperature, you have a very large gap due to spin space due to spin orbit coupling, but anisotropy gap before the A type of spin wave appears. But when you have this spin reorientation, when you go below from 80K to 2.5K, the system become gapless. You basically can see this anisotropy gap disappears, and that's when the anomalous Hall effect occurs. So what we're thinking, in this case, that the story is somewhat very similar to the case of ytterbium manganese specimens, in the sense that the anomalous Hall in here again is not caused by the static long range order, but rather caused by spin fluctuations very close to zero energy and its interaction with ytterbium moment. I mean, because ytterbium in this case is also not ordered, can give rise to anomalous Hall effect. So in both experiments, we basically have sort of discovered a way of producing anomalous Hall purely due to dynamic interactions that gives rise to dynamic non-zero spin scalar clarity in real space that can give rise to so-called the fictitious field, and that can give rise to anomalous Hall effect. Yeah. And we can do the same experiment, in the case of in the case of iron tin, when there's no moment, when there's no ytterbium moment, right? In the case of iron tin, the moment is entirely in the AB plane, and you can do anomalous Hall. It's not there, right? Because the gap is about 1/2 millivol. It's not there. There's no anomalous Hall in the iron tin. Yeah, so that's sort of and basically this is sort of the argument. And again, it only occurs in the in-plane field, and we can basically think about ourselves having a dynamic spin scalar clarity, and then for the in-plane field, the field again sets the direction. It's symmetric, sets the direction, and then that can give rise to a non-zero spin scalar clarity dynamically. Yeah, so that's sort of the two things that we've been working on, recently. Yeah, one is published, one is yet to be published. Yeah, thank you.
Okay, questions? Further questions?
And these systems, if you have this chirality, I mean, it seems like these systems are also close to maybe some skirmion physics. So do you think you can drive them, stabilize some skirmion crystal phase?
We actually for this particular material, I mean for the for ytterbium manganese specimen, there's no way it had skirmions. It's all collinear, right? There's no frustration. So even for the yttrium iron germanium, we look for skirmions. Those small neutron scavengers is not. We look throughout the space, we couldn't find any.
No, but you only get this non-zero S dot S cross S if there is some non-collinearity.
Yeah, but we're arguing it's entirely dynamic. Because skirmions is static. Right?
Yes, but okay, you have these dynamic fluctuations, right? But can you drive the system maybe to stabilize something static and get the fermion crystal or something?
That's a hard question. I don't know. Yeah. I mean, I have to admit that all the neutron scattering measurement done is at zero field. I mean, this particular one is done at a field, but it's purely looking at elastic. We haven't done any inelastic measurement, under the field. Yeah.
Good.
That was just a question regarding terminologies.
Yeah. Sure.
As to what we should be calling anomalous Hall effects.
Sure.
Say you do require some magnetic field.
Yeah.
But it's in plane.
Yeah,
The
yeah.
anomalous Hall effect would correspond to an out of plane magnetic fields Hall effect. So hence you call it anomalous.
Sure. Yeah. So basically, the anomalous Hall was typically, people say anomalous Hall is basically you have to topological Hall, you have to extrapolate to zero field, right? But this thing is being but this thing is intrinsically when you get rid of field, there's nothing there. It's completely symmetric, right? So we also use the same argument from the case of iron germanium. So we basically, if you turn on the field, it's there. But if you extrapolate, assuming the field, go to zero, it has a finite intersection.
So is it an out of plane field? So you an out of plane field, so
The field is in the plane.
in plane.
It's in plane. Out of
It
field.
doesn't break the universal with respect to
Yeah. No. Only the in-plane field. Yeah.
So
Yeah.
like that spontaneous.
Yeah.
So what is the temperature dependence of the in-plane anomalous Hall effect for this?
This particular compound, we have a complete map. The right corner.
And that coincides with the spin orientation.
Yeah.
And also when the magnets become gapless.
Yeah. We've shown conclusively with neutron scattering that this is the detailed temperature dependence of the gap, and then we look at different cuts, and then when the gap disappears, and this thing pops up. I mean, it's a correlation, right? We haven't proven, like you were asking, right? We haven't done the measurement to prove at a certain magnetic field we have the dynamic, spin scale, because neutron doesn't measure that. Neutron only measure two spin correlation function, right? So you have to argue, right? Yeah.
Okay, so for a nematic compound, spin waves, again,
Which one? Which compound?
the iron germanium.
Pure iron germanium, yeah, sure.
Flat bands formidable because of in-plane ferromagnetism. Questions for the out of plane.
Sure.
Spin waves are gapped above this reorientation, you said?
No. This particular compound has ytterbium in it. For pure iron germanium, it's always.
Yeah, the one with determine.
Oh, okay, yeah. I thought you mean this one. Yeah, this one is above 80K, it's gap, and then below 80K, the gap disappears.
And that's the reorientation.
Yes.
Should I think about this just the Goldstone modes appearing? That's why it's gapless below 80 Kelvin.
No, because the interaction between the ytterbium and the manganese moment, even though ytterbium is not ordered.
So what is the origin of the spin gap? That must be some.
Oh yeah. The reason is spin gap is typically the axis direction, like spin space anisotropy. Yeah, spin of a coupling, right?
So then why does that disappears below certain temperature? You say it's because
The ytterbium moment in this particular case, because ytterbium, even though it's not ordered, it interacts with the iron moment. It reorients at lower temperature. It wants to get ordered, but it doesn't have enough energy to get ordered. So then what it does is to re-rotate the spin from C to the AV plane.
You have the susceptibility to show us the ytterbium, what the ytterbium ions are doing. They should be Curie Weiss-like and have.
Yeah, but susceptibility, you measure the whole thing, right? I mean, you measure both the iron and the, so you cannot separate.
Right, but the iron is very good, but the iron is ordering. So iron is ordering ferromagnetically or
Anti.
So we should see the Curie Weiss.
Oh, you mean
of the ytterbiums
actually, I don't.
over and above that, right?
Yeah, we measure stability. I mean, I don't even remember what it later looks like. Yeah, to be honest.
So how do you know the ytterbiums are floating free?
Oh, because we check the low temperature with neutron scattering. There's no additional peaks of any sort.
Yeah, but did you do the bulk susceptibility measure?
Yeah, I'm sure we did. I mean, I just don't remember what the data are. I mean, no, wait. I mean, people have done this. Oh, these are my condition.
Yes. Right. Let's have a look at M divided by B. Hang on. So you've got some metamagnetic feature.
Yeah, this is spin flop. When they turn on the field, it's a spin flop transition.
Yes. So
Let me look at the stability data. This is stability. That's a stability. DC stability.
okay.
So you can see when the spin reorientation occurs, for CX field implant, you have sudden changes.
Yeah, but I'm not seeing which is which, the right-hand side and the left?
The most left-hand side, that's the stability is a function of temperature for CX field, for implant field. And then the middle is stability, sort of.
Okay, so you have an in-plane field susceptibility that's diverging, but everything else is very flat.
Yeah. I mean, on the right hand side, the stability is a function of temperature, right? For higher temperature.
So,
Oh wait, one is lutetium, the other terbium. Sorry, which one is which?
Both of them are
total.
It's a total.
No, then
It says lutetium underneath. Is one of them lutetium,
The
the other
middle one
terbium?
must be some.
Yeah, this one, sorry, this one from lutetium. Yeah, this has no transition.
Okay, so
Yeah.
So the terbium doesn't show any Curie-Weiss behavior.
Oh, you mean a high temperature?
Yes.
Yeah. Okay. Yeah.
So, are you sure the terbium is 3+ with a local moment?
Yeah, we did chemical analysis in 3+. Yeah.
I know, but where's the moment in the susceptibility? It's not there.
That's a really good point. I mean, well, you can see clear change, right?
Sure, but I'm not seeing it means it's correlated already above 300 Kelvin, or it's not there at all.
Well, there's no moment here, right? Lutetium has no moment, right? This compound has no moment. It's entirely coming from the arc.
Right.
And then the left is showing the ytterbium,
Right. But I'm just. You said that the terbium was kind of. You used the.
Oh, this is the chemical analysis to show that the ytterbium it's a 3+.
Okay, but if very nice, but a consistency check on that is you see the local moment, and we don't see it. Unless that's chi-inverse. Is that chi-inverse perhaps?
No.
It's not chi-inverse. Okay.
No.
So where there's no local moment there. Maybe it's chi-inverse. Mislabeled. Then
I don't know. I mean, I don't think so. I don't think so.
If I may comment, so there could be situations similar. This reminds me of another material where you have F moments, in that case neodymium, and you have D electrons, in that case iridium. So neodymium iridium, complicated interpenetrating pyrophore lattice. But to the point, you can't really measure easily neutrons because iridium is a bad scatterer.
Sure. Absorber, yeah.
Absorber. But there is, from ceramics, you see that there's a phase transition, iridium moments order. Neodymiums, you don't see anything until low temperatures, like 4 Kelvin.
Yeah.
But let's say if you spark yourself at 50 Kelvin, what will you see? You wouldn't see any Curie-Weiss or Curie divergence from neodymium because they are in an active field of iridium. So you see some complicated mass. It's not Curie-Weiss, even though neodymium, iridium ordered and neodymium haven't yet. Maybe it's similar here.
Yeah.
So I don't know what that case is. I'm just being a simpleton here, saying that if you've got local moments, you should see a Curie-Weiss. And I don't see a Curie-Weiss, so I don't think you've got local moments.
Well, I mean, like I said, the squid measures the whole thing, right? You measure the combination of you may basically you have to add this. You have to add the lutetium and germanium, together with the ytterbium moment.
No, that's a separate material.
I know, but I mean, the structure, the magnetic structure is the same. Crystal structure is very similar too. So you can see even in the.
I would say the lutetium system, the ions do have moments because I can see a Curie-Weiss. Unless it's a disorder-related feature.
No, there's no disorder. I mean, because we know the iron disorder because we measure autoparameter, we measure neutron scattering, we can determine what the iron moment is, right?
So on the right-hand side, you see a Curie-Weiss behavior for B perpendicular C.
Sure.
But on the left-hand side, you don't see nothing. So it's not there.
I think maybe Andrea has a point. It could be because you're seeing a mixture because the squid is not a good measurement, right?
But if the if the combination of the terbium and the iron gives you no net moment, that means they are correlated into a state which has no net moment. In other words, the terbiums are not going.
Well, I mean, we measure neutron scattering. We know are not ordered, right? I mean, we know there's no additional Bragg peaks.
What's the melt temperature of this compound?
I think actually very high. The new temperature for the iron order is very high.
So obviously the
Uh,
terbiums are ordering 2 at that temperature.
No, ytterbium has no moment. I mean, it has a moment. Has no order. Has a moment, but no order. Misspoke.
Okay, all right, well,
Yeah. It's
you're asking me to believe in you.
500 Kelvin.
Yeah, but
Here is 500 Kelvin. We measure the order parameter.
right, but one more time, you don't see a Curie-Weiss behavior. And it means that there's no net free moment there. Okay, maybe the G factor is 0. That's the other possibility, but apart from that, there's nothing there.
No, but we measure with the scattering. I mean, you can see the
So there's an ordered moment, but there's
Yeah.
no neutron scattering cannot measure the presence of a fluctuating free moment.
Sure.
But susceptibility can, and you're not seeing it there. So the susceptibility tells you those are terbiums, if they indeed are in a 3+ state, they're ordered, or if they're not ordered, then they're probably not in a 3+ state. I'm just saying it's just what your experiment is telling us. We're not
Sure.
we don't need to.
No, but we chemically measure the terms, it's the 3+.
Well, this raises a paradox then, that you're not
Yeah.
seeing you're not seeing a Curie susceptibility for that 3+. So let's.
Mhm. I mean, yeah, I mean, we this now we did it. I mean, this was done some time ago, like 20 years ago. I mean, the only reason I think you have this reorientation of the iron moment can only possibly be because of the ytterbium moment, because we don't see it in lutetium. The lutetium, if you go cool down in temperature, nothing happens. It's A type.
Well, are they the same samples?
I mean, it's the same crystal structure. Yeah, same magnetic structure.
Maybe.
Yeah.
Maybe. I don't know. In that measurement way back when 20 years ago.
20 years ago, yeah.
Do you have a susceptibility for that? I mean,
maybe that was their measurement. I don't know. That's our measurement. I don't remember.
Okay, let's
Yeah.
leave it as a question.
Yeah,
Where's
okay,
the moment?
okay.
Yeah.
I'll find that out for you.
Yeah, good. Very interesting.
Yeah, thank you.
Other questions? I think we may be ready for lunch. In which case, let's thank.
Thank you.
Okay, what time do we? Sam, what time do we have to come back for?
2:40.
2:40.
About 5 minutes before that, just to set up and check.